After having talked about charges and the elementary charge, the next thing I want to really talk about, because we're ultimately going to be looking at the way charge is moving, is we're going to look at conductors and insulators. These are the different things that we use electrically to hold charge, transfer charge, and keep charge where it is. And you're familiar with a lot of these things, even if maybe you didn't know it beforehand. So first, let me talk about conductors. Conductors are materials in which electrons are free to move in response to other charges. So because like charges repel or dissimilar charges attract each other, charge is always looking to move one way or another. So there's certain materials which allow charge to move through it, namely electrons, very easily. And you probably recognize the fact that most good conductors are things that are metal. So when we talk about why metal makes good conductors, it has to do with the outer valence shell of their atomic structure, about their electronegativity, the way how strongly they hold their outer electrons. And the reality is metals don't really hold their outer electrons very strongly, and therefore they make really good conductors. The electrons can move through materials of metal very, very easily. When we talk about conductors, and that is a material that allows these electrons to move very, very easily, the excess charge, because it all is repelling each other, spreads out as much as humanly possible across the conductor, and that really drives it to the exterior of the conductor itself. So if you have a material that has some electrical charge on it, whether it's excess electrons or absence of electrons, the presence of that charge where it's concentrated is going to be on the exterior of it. And this is so that way at the first opportunity, the charge will be able to jump off the conductor itself. When we talk about two conductors, this happens a lot. Whenever you have conductors, because the charge distributes itself over the material, if you ever have two conductors that come in contact with each other that are about the same size, what's going to happen is that the charge that's totally there between the two conductors will spread itself over both conductors as if they're one material. And we see this a lot when we look at problems where charge is being transferred from one object to another object. We love putting conductors together, just trying to figure out how all this charge is moved between them. The flip side to conductors are insulators. Insulators are materials that can hold charge, but if they have charge on them, the charge is not free to move from one place to another place. And just like conductors are metals, commonly, good insulators are things like glass or rubber or plastic. And it may be not a surprise if you think about the electronics that you know that most wires or electrical things, the parts that are carrying the charge are the metal parts, like the copper inside the wire, where the insulators are bound and are wrapping that wire. The reason that is because whenever we're using electronics or electricity, we want to move charge from one place to another around a conductor, a piece of copper, or a piece of metal, but we don't want that charge to get out into the environment, so we wrap it in an insulator, which keeps that charge all in one place. So we have insulators, which keep charge from moving from one place to another. We have conductors that allow the charge to move from one spot to another easily. And the combination of the two, insulators and conductors, allows us to build things like electronics and allows the electrical world really to come alive. So I mentioned good insulators, rubber, glass, plastic, all are pretty good insulators. Paper is also a decent one. Those insulators still can hold charge. It's very, very important. Just because they don't transfer charge too well doesn't mean that charge cannot build up on them. So a lot of times we see some of the most interesting effects when insulators do have charge developed on them. But once the charge goes on the insulator, it doesn't want to move from one place to another. So even though, say, the rubberized wire that you're looking at, maybe the cord that you plug into the wall, can hold charge. There's charge moving down, the pieces of copper moving there. As soon as the charge builds up on the inside of the insulator, it's not going to pull in any more charge or not, because the charge that develops on it won't be able to move away. So it's going to fill up relatively quick. And they make good bounds to keep our electrical charge encapsulated. Let's do an example of charge moving from one object to another object. So in this example, we have two identically sized spheres on insulating stands that are positioned just like you see them. You see the A stand to the left, the B stand to the right. On sphere A, it has a charge of negative 4.0 times 10 to negative 6 coulombs, and that's going to be distributed all throughout sphere A. Sphere B has a charge of 8.0 times 10 to negative 6 coulombs. So that means the two spheres have different charges on them. Now the two spheres are brought into contact with each other. The moment that they touch, they're going to act as one total surface, and the total charge that's there is going to distribute over both of them. What we want to figure out is after they touch, how much charge and how many electrons are on sphere A. It'll be the same as what's on sphere B. So let's go through this piece by piece. Let's figure out first how much charge is between them, because once they touch, they're going to have to spread out over both of them equally. Right? So here we have the charge totally that's there in the system. We're going to add the two charges together. And if you add -4 times 10 to the -6, and you add to it -8 times 10 to the -6, what you're going to get is 12 times 10 to the -6, or 1.2 times 10 to the -5 coulombs. So that's how much charge is there between them. Because they're identically sized, after they're separated, that means both of them will have the same amount of charge on them. So if we divide that total charge in half, we end up with -6.0 times 10 to the -6 coulombs. Hopefully this makes sense, because one had 4, one had 8. If you're kind of splitting the difference between the two, you'd find with 6. And you find that in our total charge, -6.0 times 10 to the -6. Although this example is quite straightforward, you could do this with numbers that don't exactly line up as neatly as 4 and 8 being the midpoint between 6. But if you have two identical spheres, the midpoint between the two charges will always represent what is left over in the end. So now that we know how much charge is there on sphere A, I want to figure out how many electrons are on sphere A after the separation. Well, I know how much charge is there, and I know how much charge each electron has. It's 1.6 times 10 to the -19. So if I take that total charge and I divide out 1.6 times 10 to the -19 coulombs, I can figure out how many electrons really need to be there in the first place to get me to a charge of -6.0 times 10 to the -6 coulombs. And it turns out that that charge can be represented by 3.75 times 10 to the 13 electrons, and that would be our answer.